Very good morning. We are going to talk about Shannon Fano coding in digital communications. So, in the information theory, we have source coding techniques. One of the coding is Shannon Fano coding. Earlier, we talked about Hoffman coding. Now, we'll discuss Shannon Fano coding. So, this is source level coding where the discrete memoryless channel generates the source symbols with some probabilities. So if at all the source symbol Sk, there are k number of symbols. So that is represented as k. Each symbol having their probability of pk, lowest to highest probabilities. So sum of all the probabilities will be 1. Then using Shannon Fano coding, how best each source symbol is coded according to the probability that is being occurred. So we understand the source symbol is like an event that is being occurred at their probability every time. So that is what, if at all, out of 1,000 source symbols, each symbol is occurred at how many times that is being counted, and so that out of total how many times that is being occurred, and we calculate the probability. Likewise, there are different probabilities, rarely occurring or frequently occurring. So how best these source symbols are transmitted with a few number of bits or more number of bits? That is what source coding at the source level. We required average code length to estimate the efficiency, coding efficiency, whether each source symbol is encoded according to their exact probability is given. Sometimes, because some probabilities are somewhat with a small difference, all the source symbols with the different probabilities close to that probability may have the same code length. That is why the efficiency will decrease. Likewise, see here the efficiency, the minimum code length is required divided by average code length. What is average code length? So each source symbol is encoded with some few bits, and that code length is LK, and the source symbol is having some probability pk. The product of pk and lk is the product of probability and the code length of each source symbol, and the sum of all the source symbols k equal to 0 to k minus 1 is average code length. So the efficiency exactly, the minimum code length is substituted with the entropy, which is average information, h of s. This is what the minimum code length. So we find average entropy, our average information, the entropy h of s, if you know the probabilities of those source symbols. H of s, as you know, that the probability will have the probability h of s is sum of all the probability logarithmic base to 1 by probability, that is information. Okay. And the sum of all k equal to 0 to k minus 1. K equal to 0, k equal to 0 to k minus 1. This is what average information entropy. So in Shannon Fano coding, first of all the source symbols must be arranged in descending order of their probability. And we have to get the partition of the source symbol into two sets as close to as equiprobable. That is, almost the two sets must be equivalently close to the same probability. That means half of the probability. If not, must be very close to the equiprobable. So then the upper set can be represented with the binary 0, lower set can be represented by binary 1. Likewise, we need to partition till we reach two sets only are available. The example of this Shannon Fano coding, if the source symbols A, B, C, D, E, 5 symbols are taken with their probabilities, corresponding probabilities 0.4, 0.2, 0.2, and 0.1 and 0.1. So these source symbols may have different probabilities, but however, that must be arranged in the decreasing order. Okay, if the probabilities are not given in the this order, so accordingly, those source symbols can be arranged in decreasing order. So this is the prime requirement. This is the probability. So this is S source symbol. And first step is you get the partition into two sets with their equal probabilities. So here the sum of all the probabilities will be equal to 1. And 0.5 and 0.5 divide with the 0.5 and 0.5, but there is no chance of getting 0.5 and 0.5. So this is what 0.6 and 0.4. This is what very close to equiprobable. So this is where the first set, upper set, and the lower set. This is what so this is what the first set, and this is what the second set. Upper set is coded with 0, all zeros, A and B upper set coded with the binary 0 as we assumed, and the lower set C, D, E are coded with binary 1. So this is not a mandatory. Upper set you can encode with 1 and the lower set you can encode with 0. So now my assumption is upper set is binary 0, lower set is with the binary 1. Okay. And now if this again upper set having two symbols, two variables, A and B, and again you get the subset with the two partition, 0.4 and 0.2 probability. Obviously, there is only one division of upper and lower division, lower set with 0.4 and 0.2 probability, even though the probabilities are not same. So in this subset, upper set A will be encoded with 0 as in the previous case, and the lower set B encoded with binary 1. And this lower set CDE subdivided into upper and lower sets, two partitions. In this part 0.2 probability and this lower 0.1 can be one set. So this is now equal probabilities. We got 0.2 and 0.2. So this upper set with 0 subset, lower subset is 1 and 1. So D and E. Okay. And these are all only single elements. Now these two elements D, E will be once again partition into subset, and upper probability D, upper set is with the binary 0, lower set is binary 1. Now it is very convenient to divide the each set and subset, and accordingly that corresponding source symbol is encoded either 1 or 0 based on upper and lower sets. subsets. And now, if you consider the total binary bits of A 00 is encoded for binary, the symbol B 01, it is encoded 01, C 10 encoded with 10, D with the 3 bits 110, 110, and when a symbol E encoded with 111, 111. See, here the highest probability of A is encoded with the 2 bits, lowest probability D or E encoded with 3 bits. So long bits, and this is short bits. But here, even though probability 0.4 and 0.2, 0.2 and 0.2 B and C are also having two bits, and also 0.4 probability having also with the 2 bits, encoded with the 2 bits. So there is some lagging in the efficiency while encoding. The same number of bits are encoded with either 0.4 or 0.2 probability. But in our coding analysis, highest probability will have the shortest code. So this is not happened less than 2 bits. In this case, that is how the efficiency slightly will decrease. We find that efficiency, the minimum code length divided by average code length. Minimum code length is equivalent to entropy, average information, divided by average code length. So the entropy you can calculate H of S as the formula which is given P of K into logarithmic base to 1 by Pk. So that is logarithmic Pk is minus of that. So this minus is given because logarithmic base to 1 or logarithmic base to 1 by Pk. So H of S is H of X is Pk logarithmic base to 1 by Pk, which is nothing but this is minus of logarithmic base to Pk. So for each source symbol with their probabilities, we can take the multiplication and sum of all k equal to 0 to k minus 1. So all these, so we got 2.12 bits per symbol. This is what average information entropy and average code length, because the see here the code length LK of each source symbol. This is what so this is what the code length LK. So this is what 2 bits. This is what 2 bits, 2 bits, 3 bits, 3 bits. So this is where P, K or LK, RPI and LI. So this is where the average code length. This is what in place of I, you can take a PK, LK, anything, any notation. So this is K equal to 0 to K equal to 0 to 1 to M or 0 to M minus 1. Okay, K minus 1. This is what K minus 1. 0.4 multiplied with this 2, 0.2 multiplied with 2, and 0.2 multiplied with 2. Likewise, we can get the summation to 2.2 bits per symbol. So the efficiency is entropy divided by average code length 2.12 by 2.2, 0.96 into 4. So into percentage, you can get 100% in case of this percentage 96.4%. So this is slightly decrease the efficiency because of the highest probability with the even 0.4 encoded with the 2 bits as similar to B, symbol B with a 0.2 probability. That is why the slightly difference is there. That is the coding efficiency. That is how all the source symbols estimated with what are their probabilities, and those symbols are arranged in the decreasing order of their probability, and we get the partition of equal probabilities into two sets, each set, upper set and lower set, binary 0 and binary 1 encoded, and each set subdivided into subsets till we get only one symbol. So each subset, again, upper and lower, is encoded with 0 and 1 and 0 and 1 and 0 and 1. And all these bits are assigned for the source symbol as this. This is how the transmission happened for these source symbols with the code of source binary bits of this. So this is how the Shannon Fano coding. So the based on the probability, and we can get how best that is being coded according to their probability. We can estimate the coding efficiency. Thank you.